All right, today I'm going to show you how to do a Hardy-Weinberg problem, why we use them, what the variables mean, and hopefully after you get done with this, you'll have a good idea if you ever have to see this again, which if you take AP Biology, you definitely will see these again. And hopefully you can benefit from my experience on how to do these correct and so you don't get them wrong. So if you look at the equation, the basic equation that they came up with was P plus Q equals 1. Uh, and this was to determine frequencies. Some geneticists saw this and read about what Hardy-Weinberg was trying to do and realized, hey, most genes, there's 2 alleles. I think that this might help us figure out frequencies. So they talked to them and they said, yeah, that would probably work. Because there's 2 alleles for each trait, though, you need to square the equation. So that's going to be P squared plus 2PQ plus Q squared equals 1. So basically, this is the idea that you got 2 alleles for a trait, and this can help tell us the frequency for that trait. So what do they mean? Well, P is the frequency of the dominant allele. Q is the frequency of the recessive allele. There are some people that will use these interchangeably, where they'll say, oh, it doesn't matter what P or Q is, you just know it's one of the alleles. That's great, but you should probably spell it out so you know what's what. This is usually where people screw up at. They keep putting the wrong number under P or the wrong number under Q, and things get a big mess. So it's best just to say and keep it consistent so you don't screw it up. So I always focus as P being the dominant allele, Q being the recessive allele. All right, that's for the frequency of just having one allele. What happens if we were looking at an actual person, or what's the percentage of people that have a particular set of traits? So that's where the P squared comes in. So P squared is the percentage of individuals that are homozygous for the allele P. In other words, they got 2 P alleles, whatever that would happen to be. 2 dominant alleles is what I'm calling it. Q squared is basically the opposite number in which it has 2 of the recessive alleles. It's the percentage of people that have that. And then finally, we've got the heterozygous people here, 2PQ. So they have 1 dominant, 1 recessive allele. And the 1 just stands for the 100% of the population. All right, so if you keep those variables straight in your mind, that should help you in solving these problems. Keep in mind this only works for 2 alleles. If we had 3 alleles, say blood typing, we have A, B, and O, we would have to expand this equation. I think you'd have to cube it. In other words, you'd have a total of 5 different alleles in which you'd have blood type BB, blood type AA, blood type AB, blood type AO, blood type BO would all be in there. So we're going to stick to just 2 alleles for simplicity's sake. So I'm going to do this first problem for you. So this is the paper you're going to be working on. As I do this, this equation will be up there for you to see. If you follow this procedure, you should be able to figure out the equation and get the answers that you need to do. All right, so we have a sampled population. We know the percentage of homozygous recessive genotype, little a, is 36%. Keep in mind, whenever we do Hardy-Weinberg problems, we're always looking at the recessive allele. Why? Because we can count those individuals. Those individuals are different than the other 2 groups. The heterozygotes and the homozygous dominant, they look the same. We cannot tell the difference between them, but we can separate the recessive ones out there. So that's what we start with. All right, so change my color here. So little a basically equals 36% or 0.36. We always change it to a decimal. And keep in mind, little a also equals Q squared. So it's going to be the Q squared one that it will equal. All right, so there's our first answer. Q squared or little a 0.36. All right, B, we want to know just what's the frequency of having one little a. In other words, we got to solve for Q. So how do we get Q from this? Well, we have to take the square root of Q squared. Change this here. All right, and that's going to equal the square root of 0.36. All right, and so basically that's going to change this to take the square root of Q squared. We end up with Q. And if we take the square root of 0.36, that's going to be 0.6. Remember, whenever you square root a decimal, it's going to get bigger. It's going to be a bigger number. All right. Step C, the frequency of having a big A. So big A is equivalent to P in the equation P plus Q equals 1. So P is going to equal 1 minus Q. That's pretty simple algebra. I think you all know that. So that 1 minus 0.6 equals 0.4. So pretty simple there. So we're using the original equation. We used the simplest equation we need to use to get our answer. So we knew what Q was, and we know we have the variable Q in this equation. So we can just use it there because they're related equations. All right, now we got to find big A, which is also P squared. So P squared equals 0.4 squared, which is going to equal 0.16. All right, and finally we got step E, our last step. So we got to find the heterozygote, so that's 2pq, and I'm glad I don't have to do any more squares here. So that simply equals 2 times 0.4 times 0.6. All right, now here's where a lot of people screw up. Instead of putting p and q here, they end up putting q squared and p squared here. So you got to watch that. A lot of things messed up. And usually when we do a Hardy-Weinberg, we're trying to figure out big A, little a. All right, anyway, if these two numbers don't equal 1, you screwed up. So that's the thing you need to watch for. So when you multiply those, it's 0.48. And that's how you solve a Hardy-Weinberg problem. All right, so that'll be up there for you to review if you need help for these other 4 problems that you need to work on. All right, so I'll give you a few pointers on these and what I want for each problem. So problem 2, you're going to read all this about sickle cell anemia. Got 2 traits. You got the sickle cell gene and the normal blood gene. The key number after reading all this is this 9%. So that's going to be your Q squared, and that's what you're going to start to work for. Keep in mind when you put 9% into a decimal, it's 0.09, okay? Up if you miss that. So when you end up reading this, you need to find out how many people are heterozygous, or what is 2PQ. That's what you need to find in this problem. All right, problem 3, we are going to look at the ability to taste PTC. So you either have the dominant T and you can taste it, whether you're heterozygous or homozygous, you will taste it. If you're little t like myself, you cannot taste it. So when you read this, you see you got 215 students in biology, 150 can taste it. So that's the heterozygous and the homozygous, not a useful number. It is the 65 that cannot taste it that's useful. That's going to be your Q squared. At least it will be when you take this 65 and divide by 215 so that you get your decimal. And that will be your Q squared. So that should be easy to get Q squared. Then you just got to find P squared and 2P. Problem 4, cystic fibrosis. Again, this is you got the recessive trait and the dominant trait. Basically, the recessive trait, we see 1 out of every 2,500 babies. Therefore, 1 divided by 2,500 is going to be your Q squared. So again, you need to find Q, P, and then a 2P squared because we really want to know the heterozygous individuals. And then finally, we got problem 5 here, in which we have 19, you and 19 of your closest friends. That means 20 people are on a plane. They just happen to be 10 males, 10 females. You're going to start your new population. It turns out 2 of your friends carry a recessive cystic fibrosis allele, meaning they got 1 allele. So what you need to find is Q squared, and you don't have that. What you have with those 2 people is you got 2PQ. So you know that, and I'll even put it here, 2PQ equals, let's see, 2 divided by 20 would be 10% or 0.1. All right, that's not a useful number for you because from that, we got to figure out Q and P. You're not going to do it. It is not useful. So I am putting that in there so that I can strike it out so that you don't do that. Do not use that number. What you want to look at is the other 18 individuals. What are those people? And how is that the opposite of Q squared? All right, so there's just some pointers on how to do these problems. If you have any questions, feel free to email me. Let me know what's going on. You'll find this form on the Google Classroom, and you each will have your own copy, and hopefully it won't be screwed up like the DNA format was, or the DNA decoding thing I gave you earlier. All right, that ends Hardy-Weinberg problems.